going to continue on our journey of IOE in utilities. So we started the morning session for utilities with an overview of IOE and all the endless possibilities, but also it's a lot and it's large, but it's a big opportunity. We saw some big numbers. We saw David show us what BC Hydro's pressing business challenge was, distributing the energy, bringing it from one end of the province to the other end, a very diverse group of customers, and dealing with some significant numbers of electricity theft. We're going to take it to a level deeper. We're going to look at what Itron is doing with developing the technology to bring it to the next level, to get the smart grid solutions to the next level. And Paul is going to tell us all about that. And then Ronnie will follow with some examples of how we explore further use cases and have a conversation with you. Where do you start? Because if it's this big, it may be too overwhelming. So how do you make a choice of where to start? And Ronnie is going to talk about that during his presentation, or at least give you some pointers of where you can start or what considerations to make to start. So Paul is Director of Smart Grid Solutions for Itron in Asia. So thank you very much, Paul. And take it away. Do you want this one or that one?
We need the clicker for the slides.
Everybody there?
Yep.
Good.
Got it.
Thank you.
Okay. So, hi. Thanks everybody for coming. I'm gonna talk today really about. Okay. Trying to make the clicker work. There we go. So how do we move beyond AMI with the Internet of Things? And I think Dave kind of started us out on this on the journey, where he started out with a fairly typical smart metering solution from Itron that was completely focused on the meter to cash application, but only through the engagement of Internet of Things technologies, of IPv6, of some of this multi-service network concept, do we really start to realize the value of true interconnectivity inside the utility. So, you know, what are we all looking at across the industry? I think the challenges are pretty much the same whether you move to, whether you're in Asia or the US, it's degrees of challenge. So there's increasing demand. Everybody has more appliances, they want more air conditioners, they want more power, and they want it pretty much all the time. So in places where you used to have 4-hour power, there's a move to get to 8-hour power or 24/7 power. In places where you have power all the time, you still want to get the outages down. The fuel costs are rising. I mean, even despite the low oil prices today, I think the general trend in thermal fuel costs and nuclear generation costs is upward. We have cheap new energy sources in solar and wind, which are coming in, but those introduce a degree of variability into the grid that old Edison-style electricity system, where you have the big generator over here and the small load over there, wasn't really designed to cope with. You need to react faster, and you need to react more locally, right? In Australia, they've got transformers that are getting overloaded by solar panels backwards. So from the low voltage to the medium voltage, you're exceeding the rating of the transformer with excess solar generation from the houses. You're seeing the load curve actually invert. So at 4 in the afternoon, when you used to have your peak, now you have a trough. How do you deal with that? How do you manage that as a utility? This can destabilize the grid. So these new energy sources present a massive opportunity, but they also present a massive risk to the stability of the grid itself. So what are we talking about when we talk about smart grid? Everybody's got their own definition, right? What is smart grid? What is smart metering? Well, I have a smart friend. How smart is he? Is he a genius? Is he kind of smart? Is he smarter than you? Is he smarter than me? So the best definition I can find, right, is this one, which is intelligent integration of all the stakeholders and their actions to be able to react to whatever they do in a sustainable, economic, and secure manner. So there are certain advocates which will say the industry is going to move all to island grids, where you're going to have everybody's going to go off grid, they're going to have their own solar panel, their own generator, and a bunch of batteries, and who needs the grid? The whole grid is obsolete. The flip side of that is all this solar stuff is just causing problems and it needs to go away and we'll centrally manage it. The truth, as always, is somewhere in between. So when we think about the journey from advanced metering, or AMI, to smart grid, we have to look at what was the first round of technology. The first round of technology in advanced metering infrastructure did two things very well. It measured and it communicated those measurements back to the head office. So the whole point of advanced metering infrastructure was to get better data for your meter to cash process and to enable the consumer to engage somewhat in that conversation. Right? So the benefits were quite high, right? We talked about the benefits of AMR all by itself, just remotely reading the meter. You got meter reading benefits, you got customer service benefits in that you could check that the meter was online before rolling a truck, and that you could actually help a customer resolve a bill complaint on the phone by explaining to them what their load looked like, right? And as we moved into AMI, we put in the disconnect switches. We put in a little bit more intelligence to bring back some additional data about the consumer. We put devices in the home that could connect to the meter and show you what your energy use was over time. And really, if you look, at least in North America, the first round of this was predicated very heavily on demand response and energy savings. So the California utilities, some of the Northeast utilities, based a lot of their business case on the ability to shift peak load from A to B. And this was back in the 2005, 2006 timeframe. And then add on top of that a bit better outage response. So these were all very good benefits, and you can see there an annual benefit of between $12 and $25 per customer per year once you stack all the benefits on top, depending on the utility and the business case. But again, fundamentally, this was focused on the meter to cash process, right? And there were a few reasons for that, right? So some of the limitations here, this is still a very central system approach to smart metering. You bring the data back to the center, you do what you have to do, and you push it back out. There's a certain amount of latency in any system that's designed that way. And you can't afford to put low latency networks to 1.8 million customers or 2 million customers, because the data you're getting out of it isn't quite that valuable. So the response times are better, but there's still a fair amount of human intervention in the output of these systems. Part of it is because as an industry, we're still learning what all the data is and what all the data means. There's pattern out there in the usage, but we're still kind of differentiating the signal from the noise. So what does a particular voltage pattern indicate at a customer level, at a segment level, at a medium voltage level? And then the operational and safety benefits of a lot of the early AMI implementations were limited by a lack of integration to the operational systems. So again, as you look at smart metering, if you look at smart metering as a single application, you miss out a whole lot of the benefit that comes from integration. You look at most of the smart grid programs that have been run, and while the big ticket item is the smart metering, and they spend a huge chunk of change on that, they spend almost as much money, if not more, on IT systems, on back office integration, on changing the business processes that they've built over the last 50 years in their utility to adapt to the fact that stuff that used to take a day and require a work order now can be done at the push of a button. A lot of the early AMI started with just, let's put the metering in and then we'll figure out how to integrate it to the rest of the business, right? And I think that you see in the successful programs that they took the opposite approach. They said, what's our end state vision and how do we get there, right? So So what is the end state vision? And I'm talking a bit of a difference here between AMI and smart grid. So AMI, which is kind of version 1.0, was a lot of meters sending a lot of data back to the central system. The value creation was focused mainly on meter to cache. Smart grid 1.0 was where they started to collect a lot more non-revenue data, so voltage data, non-billing determinants. They started to look at the distribution side benefits and maybe merge the two data sets from their distribution management system and the smart grid to see if they could get some overlap and some interplay. And there were analytics in the back office primarily. There was nothing you could really do to take action. These were day ahead or 2 day ahead systems. So we'd get all of yesterday's data, we'd look at it, and we'd see what we could determine from it, and then maybe we'd take action today or we'll take action tomorrow. It wasn't a real-time system. It wasn't necessarily real-time response. So where we're going, and again, I think Dave articulated this very well, and what BC Hydro is doing is kind of leading the way in this, is coordinated analysis and action at the edge of the network. Because if the voltage on a segment or below a transformer is fluctuating and you're losing voltage or your frequency is changing because you're injecting so much solar load, you don't have the 10 seconds round trip to go back to the office and come back down. You've got to start to cut off the offenders now. And you can't cut them off one at a time, each with its own little program, or you're going to cause other surging problems in the network. So you've got to have a coordinated response that's coordinated locally. So where does Smart Grid 2.0 take us? It starts to move us out of the customer side and really into the grid side. So in order to really start to recognize the advantages of the grid, to the grid, of this technology, you have to have more real-time data, you have to have better connectivity, and you have to have smarter endpoints. So what is this? What are we aiming for here, right? So I kind of want to talk about a couple of things. If we look at hardware in meters, from the time Itron started in 2007 until 2011, when we started and built the meters for BC Hydro, you saw the computing and memory power in these platforms increase more than 10 times in 5 years. So this is pretty consistent with Moore's Law, right? The processing power you need to do the things you want is going to go up over time. The good news is that same processing power continues to get cheaper. So you're able to kind of maintain a consistent cost base in the meters while adding power and functionality to those meters. But the biggest thing that we're adding here is not necessarily a specific function. It's future-proofing. These meters are going to be in the field for 15 or 20 years. It's not like a cell phone where you get to throw it away every 2 years. The regulators haven't got there yet, and even if they did, you couldn't actually replace them fast enough to do that. And some of the fastest replacements we're seeing around the world is 10 years. And even that is a challenge, right? You're in a continuous project mode at that point with meter rollout. So you've got to look at the platform as something that's going to be in place for 20 years. And what is the Internet of Things going to look like? And imagine using your cell phone from 20 years ago to do anything today. It wouldn't work. It wouldn't even work on the networks that exist today, right? Your cell phone from today, on the other hand, because the radios in it are programmable, because it's got a lot of extra memory and RAM, it has a chance 10 years from now. The good news is that sensors are slightly cheaper than smartphones, and we have a better idea of what the problem space is in the grid 10 or 15 years from now than we did about how people were going to be using smartphones. But I think you have to take that into consideration, which is, what is this going to look like 10 years from now or 5 years from now? So what else does the Internet of Things give us? Well, a couple of things. Computing power is getting cheaper and cheaper and cheaper. There's a microprocessor in everything. They use less power. They take less silicon. There's new communication capabilities out there. So as we move forward with the standardization, and we're able to do multiple modulations, not just single modulations on a radio mesh, We're able to use multiple communication technologies within the same modules. We've also figured out how to understand locationally, so the meters and sensors on a grid network can actually figure out, electrically anyway, who else is near them. So you can look at the patterns in the usage, and you can actually determine what meters are below the same transformer, and you can group them all together. Right? The last thing we need to get to is multilingualism. So in the past, even smart meters spoke one protocol. It could be NCC12, it could be DLMS COSM, but they were going to speak one protocol. The meters of the future are not just going to have to talk to meter reading systems. The meters of the future are going to have to talk to distribution automation equipment. They're going to have to talk to reclosers. They're going to have to talk to cap bank controllers. And they don't speak DLMS COSM. And DLMS COSM isn't a very good protocol to talk to those devices. They've got our own protocol, IEEE 61850. So ultimately, we're all moving towards some standard protocol. But until then, the devices are actually going to have to be smart enough to know who they're talking to and speak in the language of the other device, or listen in the language of the other device. The other thing that we've gotten over the past 5 years, really, from the Internet of Things and the Internet in general, is a standard stack that is pretty consistent now across the industry, across all industries, where we're looking at, you know, IETF for the IPv6 and the network layer protocols. We have the IEEE defining at a pretty low level the physical layer and MAC layer protocols that are the way towards interoperability. You know, Dave spoke about the Cisco Developers Network. The whole basis of this future is that the network is ubiquitous and the network is open to new devices, not locked into a single manufacturer or a single protocol. So what does this look like when we realize the vision of Smart Grid 2.0, right? So the first thing you'll notice about this is we're not just talking about electricity meters anymore. We have to expand the conversation to electricity, water, and gas. We also have to expand to other public services. So when a power line goes down, for example, and you have a high impedance fault, so the power line is down, it's still live, what do you need to do? Well, you need whatever first responder is in the neighborhood to show up and make sure nobody touches that power line while the utility figures out how to switch it off without blacking out half the city, right? And if you can make sure there is a first responder on scene and he can communicate back that he's there and nobody's in danger, you don't have to switch off an entire medium voltage feeder, which could take out tens of thousands of homes. You can do a lot more mitigated, nuanced switching. You know, water utilities are one of the biggest users of electricity in any community. They pump a huge amount of electricity to make the water come out your shower head at high pressure, and those things are interrelated. The losses in water translate directly into wasted energy, wasted money. A whole bunch of things now are starting to be interconnected. So what does this really look like? We have intelligent meters and sensors. So these aren't just devices that read a value and spit it out to the system. They look at the value, they have the processing power to analyze forward and backward, to look for their own patterns. This is particularly useful in theft analysis and revenue protection, where just because somebody opens the terminal cover on a meter doesn't mean it's been tampered with. But if somebody opens the terminal cover on the meter and the load goes down, then you can be pretty sure that a tamper has occurred. Now, where is the most efficient place to do that analysis? Because in today's paradigm, we're bringing that data back to a central database. We're looking for the patterns mostly automatically, and we're identifying them and we're sending somebody to the field to look for them. Wouldn't it be better if the meter could just tell you, here's my tamper, here's when it happened, here's the load profile around it. Then I haven't had to collect a huge amount of load profile from every meter. I can actually build the intelligence into the meter to identify when it's been tampered with. If I'm certain enough that it's been tampered with, I can have it turn itself off and send a message until somebody comes and looks at it. And So while that's a case for non-technical loss, that's also a case for safety. If somebody accidentally opens the meter, or a wire gets yanked out and is dangling live and you've got a lost phase, you want to know about that as quickly as possible, and you have the opportunity to do something about it. The more we take the human beings out of this interaction, the more likely it is to happen. Right? So again, location-aware devices. So if you know who's next to you in a power outage, for example, and he goes out and you don't, and you're a reasonably smart meter, you could say, hey, I know for a fact that the whole segment isn't out. It's just an isolated outage. Could be the guy turned his meter off. So you don't have to send the information to the outage management system. You don't potentially create a work order that doesn't need to exist. And so the interrelation of this data is where the power comes from, right? I think that's what everybody said this morning. It's no longer about can we get the data, or where do we put the data? It's how do we use the data, and how do we make the data work together? The other problem that was pointed out is we don't have enough bandwidth or enough storage to bring all the data back to the middle and look at it and process it there. We have to start to process it out at the edge, right? And we started with mainframes, we moved to mini computers, we moved to PCs, now everything's moving back to the cloud, and then everything's moving back from the cloud to the edge, right? So it's sort of an unending cycle where we keep trying as an industry to get it right. How much should be central, how much should be at the edge, and it all comes down to these innovations in the underlying technology and the ability to connect. So the connectivity is there. The processing power is becoming inexpensive enough that you can truly start to think of a meter as a grid sensor or a grid device, a participant in the conversation between the distribution automation and the distribution management and the consumer management. And since you've got to put a meter in the field anyway, right, if you can have that be a multi-purpose device, you've saved money. Ultimately, you've been more resourceful with the money you've spent. So, we talk about energy diversion. I think I just stole my own thunder on this slide. So we'll skip that. But we also think about outage, right? Today, in the AMI world, what happens when there's an outage is a meter reports an outage back to the head office, and somebody puts it in an outage management system, and they either take action or they don't based on programs which were really designed around customer call-in, right? So essentially every meter sends up an outage notification, and that gets treated like a customer is called in and said my power is out. Well, it doesn't have to be that. Maybe the customer turned it off intentionally and doesn't need to call in. Maybe it's only one customer on a segment, you don't know, right? So if you start to think about what you could do with edge computing, right? If you have, let's say you have a guest operating system in a CGR where you can run a program, and it knows what meters are around it and what meters are connected to the feeders around it. Now you can wait until you hear a second outage response, right? And you can say, okay, now I've got 2 meters from the same place that have a problem. This is when I have to send my message to the outage management system, and I can send a much more confident message that says, I have 3 meters out on the same transformer. Somebody should come look at this. That's a much more actionable piece of information coming out of the field network than a million meters screaming out as their power's cut off. Right? So how do we get there? And what are we doing to get there? So I'm going to talk to you a little bit about the Itron Riva platform. We have some meters here, and later on at the break, if people want to see kind of what we've got, we can show it to you. I didn't want to put a demonstration in the talk because that usually just takes too long. The Itron Riva platform is really the combination of a computing power and communications power into a single platform that allows you to have edge computing in your very end devices. And that works with the Cisco network and the edge computing in the CGRs to be able to actually start to move intelligence to the edge, right? So we put the computing power in the meter. Now you've got less data to bring across your network. It's got more bandwidth to do low latency tasks. You've got the ability to actually make intelligent peer-to-peer decisions because the meters are able to talk to each other and figure out what's going on in their local area before they report a problem, right? And with the real-time communication between these devices, you can actually make decisions in the field that need to be made in the field and not cause the latency to push back up. So if you know you want to take a certain action every time the voltage dips, you know, Dave's example, you could take the voltage, you could connect it to a voltage a management system, and you could just have the action taken to change the tap, assuming there's a tap changer on it. That's the next step in all of this, right? And then finally, the adaptive communications technology. So Dave talks about his one network rolled out across vast territory of British Columbia. You need to have everything on a single network if you want to have peer-to-peer communication and have it work, right? So the adaptive communications technology, again, based on the same standards that we've been talking about before of the Internet of Things, you take and you combine together the RF mesh technology that we know works and the power line carrier technology that we know works into a single network device that can actually choose to go in either direction. So if you think about the old way of optimizing, you roll out a network to 95 or 96%, you optimize the network after that to get to 99 or 100%. The idea here is that it's much more self-optimizing, right? So you have to be able to connect all the devices in order for this to be useful. And don't just think about the meters back to the head office. Think about being in a high-rise apartment with lots of concrete between you and the customer and trying to talk to their refrigerator, right? Because that's where this is going next when you bring the customers into the conversation. Being able to look and understand what's going on, having an absolutely self-optimizing network in the long run. So the idea here is that it actually dynamically chooses between radio frequency and power line carrier. And that enables it to go into some of the toughest situations that we've seen in deployments, which are large multi-dwelling units, underground meter vaults, and very low density environments. So you have, yeah.
So on that previous slide, is there an intermediary between the meter and a transformer? So how are you getting to the CGR?
Well, so again, because it depends. So the power line, so there's no intermediary between the meter and the transformer except an RF mesh hop to some other device. So the ability to, and I'll get to it in just a second, and I think we'll explain how it works, but the idea here is traditional PLC is limited to one collector per transformer. So out here in Asia, that would be somewhere between 50 and 500 meters. In North America, it's somewhere between 5 and 15 meters. And the transformer effectively stops the power line carrier signal. The problem with that is you have to roll out a ton of network equipment. And regardless of the cost of the network equipment, you still have to manage, you know, whatever your total is divided by 400 meters, which is a lot of network equipment. So the idea here was to maximize the amount of meters that could connect to a single router. You combine the two. So if it can get all the way back to the, typically your power line carrier meters connect to a transformer somewhere. And usually there's a meter or a couple of meters that can be got to without power line carrier, and they can then talk to another radio frequency meter. I've got a diagram in an upcoming slide that sort of shows you, this is the exact same slide, that shows you how this works. So again, as we look at our experience in rolling things out, it's pretty easy to get to 90%, right? It's that last 5 to 6% of meters that drive the cost of the deployment, mostly in optimization services and additional network equipment, to get to the really hard to reach meters. And again, to a certain extent, from a smart grid perspective, this sensing is not as useful if it's not everywhere, right? So I'll give you a real world example. So this is a building where we ran a part of our pilot, and it has 1,800 meters, 2 big towers, a shopping mall, a car park, and 2 substations. So the radio can't get from here to here because there's too much concrete between it, right? The radio, the power line carrier can't get between the 2 transformers at the bottom because you've got a bunch of shops, maybe 10 or 20 shops on each transformer. So if you were to do a design on this with power line carrier, because you've got 3 transformers, you need 3 pieces of network equipment. If you were looking at this from a pure RF design, you could get about 98% of the meters by putting in 2 pieces of network equipment, but you probably wouldn't pick up all the meters downstairs, which are the largest meters in the building. They cover the elevators, they cover the shops, they cover that. So by combining the 2, you've got key power line carrier links that'll actually carry all the meters from the building stacks down onto the first floor and connect them with the meters. So there may only be 30 power line carrier links in the whole network, but they hold it all together. And this is what enables it to be self-optimizing. Again, when we did similar buildings like this with an RF-only solution or a PLC-only solution, we ended up having guys spend days crawling over the building trying to figure out how to make everything connect. So the driver here isn't necessarily that you always need either technology. It's like that old joke about marketing. I know 50% of my marketing budget is wasted. I just don't know which half, right? So you never know when you go into a building like this, and particularly when you go into cities like Hong Kong, Singapore, Bangkok, Manila. You don't know what's in the building until you get in there, right? And there's no way to pre-optimize the network on a building-by-building basis, cost effectively. You have to go in and try it and see what works, and then move on. All right. So that's really that's the network side of the technology that is coming along to help make these networks easier, faster, cheaper to deploy. And at the end of the day, when you combine that with edge processing capabilities that exist within the Cisco network and now within the edge device, you have the power to write your own apps, to do all sorts of different things that optimize the system to whatever that particular electrical grid needs. And again, I'd be remiss if I didn't talk about smart energy and water kind of working together in this. These networks, once you've deployed a network, and it's a multi-service network, it almost seems wasteful to use it only for a single company. So what we start to see in the smart cities movement is people are looking at the electricity utility who's already rolled out AMI or smart grid or whatever we want to call it today. If you've already rolled out a network that's across the whole service territory, how hard would it be to really let the water company jump on it so you could read their meters and help them monitor their pumping stations? There's a number of initiatives around that are citywide or nationwide. I think it was mentioned this morning, Cisco is working on about 120 different smart cities. Itron's working in about 7. We're nowhere near as big as Cisco. But what we're seeing is this demand for a single network that you can hang parking meters and power meters and everything off of. And the power of the Cisco network is that it is truly multi-service, it is truly open and interoperable, because the sensor you need for a parking meter is not the same as the sensor you need for an electric meter. But you know what? Packets is packets, right? And so as long as you can put them all across one network, you can lower the cost of connectivity for everybody in your community. So I think I've actually ended on time. The message where I'd like to leave is that as we look at cities in the future, we have growing urban populations, we have aging infrastructure. We've got to do more with less. It's just a fact of life. We're going to have more people and less stuff for them to use. The amount of water on the planet is going to remain constant. The amount of fuel on the planet is decreasing. So we need to be good stewards of that. And one of the ways we do it is by managing the resources we have. And these are the systems that allow you to do that. That's it.
you're acting locally, but you're thinking globally, and that's what we're here to speak on in terms of the IoT. So this is a what you've described here is it's a pilot that you've got in Singapore. Is that correct?
No, we've done it.
Telecom.
Yeah.
So when do you, Itron and Cisco, and how do you bring this to the rest of the world? You know, we're thinking about standardizing to lower the total cost of ownership amongst all of us.
So yeah, I'll speak to that. I mean, so Itron has launched this technology, which is a combination of the standards, same standards-based stuff you get in the Cisco network, right? We've launched it outside of North America as our first set of markets, and that's kind of been for two reasons, right? The first is that outside of North America, there are more customers North America has got 60 to 65% of the utilities have started to roll out or have completed rolling out, and so where they're headed is optimization of those networks. In the rest of the world, there's a lot more. A lot of utilities are making their selection for the first time. And so in order to make sure we kind of focused on getting all the technology we could into the newer markets, we just made the choice to release it there first. The next step is to bring it back to North America, probably in the next couple of years is my understanding. So this was launched in August of last year at Metering Asia for the first discussion, and there is a plan to reintroduce it in metering products in North America. It's actually likely that it'll come back not in meters in North America before it comes to North America in meters. It may be in streetlights or in other technologies. This is all going to be wrapped into the Cisco Developers Network and really available to whoever needs to use it. But you got to start somewhere.
Good answer.
To take it globally, one of the things I learned is that PLC is not PLC everywhere, or it's not the same PLC everywhere. So Ronnie is probably able to comment a little bit on how our equipment works and how we're moving more modular.
So you're aware of the DevNet program, and partners can join with Cisco there to add their innovations in and insert them into the CGR routers via the available modules. And effectively, what Cisco is doing is bringing that effectively standardization approach to these partners, so that when you come to parts of the world like Asia, where things like the RF band that's available is different everywhere, the frequencies are all different, then what Cisco is doing is opening up the platform, opening up the CGR to allow third parties to invest in that innovation and effectively take that on to enable them to solve those challenges also. There are challenges that Itron found in the Hong Kong market, for example, with the RF coverage that Paul was referring to. And so here's a piece of innovation that Itron has undertaken, and effectively they're leveraging the IOX capability of the CGR and effectively solving a real world problem here. So that path is open to all of Cisco's partners, not only the ones that we have today, but future partners, including end customers.
So two parts. It's the modules within the CGR, and then using, let's say, the processing capabilities that exist in devices to add additional applications to them. Now, not everything is developed by Cisco, but that's why our ecosystem of partners, and especially more and more the edge computing application partners, are becoming so important for the success of the end-to-end solution, because not everything can be developed just by Cisco because there are so many variations. So we're looking for these partnerships, and we're looking to be able to switch out one PLC module with another PLC module from a different supplier based on what the local market requires.
So the other thing that was mentioned about the modules, the bigger innovation that's come out of the product portfolio is the IOX initiative, which is where Cisco traditionally ran iOS on that router, and iOS owned that router. It was closed. what Cisco has done now is partition the router, effectively creating a form of hypervisor, effectively like a virtual machine. And there is a portion of the compute and processing power reserved for the network and for iOS, and that is there and will always be there. The remaining resources, just like a VM farm, have now been made available for third-party innovation so that you can then load your application into that compute and memory space. That's how we're enabling that edge compute function. It's that opening up of the platform that Cisco is now doing, which is what we're trying to do, and encourage partners to come in and use that platform. And to what was just mentioned there, the different initiatives, including bring your own application or bring your own interface module and onboard it, are now available. That is what the IOX story is all about.
Good question. Yeah.
Yeah, you mentioned about the active grid network that can integrate with other disparate systems such as traffic control or emergency response. Can you elaborate in terms of how that can be done and how is it being used?
I think so. Yes, I think I can. There's a couple of things. One is, so when you think about the active grid as we've sort of framed it here, Smart Grid 3.0, the machines are making the decisions, not the people, right? And some of that is the ability to figure out what the human beings are still necessary to figure out what the rules are and the patterns are and the actions are. But ultimately, the back office system becomes a publisher of rules for the active grid. So I'll give you a couple of examples. So there are rules now in certain jurisdictions where if your solar inverter starts to creep the voltage up on the segment you're on, you have to self disconnect. If you don't self disconnect at 230 volts, then the utility will auto disconnect you at 240 volts, and you have to pay a penalty, right? So that's a very simple form of the rule where it's a single meter looking at a single set of problems and going, uh-oh, we violated a fairly simple rule set, click, got to go away. And then it's got to report that it's turned the customer off, and it's got to move, it's got to, allow the customer some time to reset, right? Because you can't keep them off forever. The more you involve human beings in that, the more it costs, right? So the idea is that these devices can make decisions and enforce rules all by themselves. If you add peer-to-peer networking to that, then devices can look at other devices in the same area. And rather than make a decision on the fact that this meter happens to be generating at a higher voltage, you can look at the voltage across the transformer and say, am I getting to a dangerously high voltage? Is this really causing a problem for me? Or can I let this guy go and continue putting energy back in? Or do I really need that energy in my local area? So even though he's over voltage, I want to cut him. If I cut him off, the whole area goes dark, right? So there's more decisions, and as we get more and more embedded generation, the grid is going to have to be smart like that on a local level, because it's not about optimizing from the transmission down to the user anymore. It's about optimizing each, if you will, each transformer, each segment kind of becomes its own little market for ancillary services, because the distributed generation can be so destabilizing. The last thing I'll say is, when you get into those situations, the end meter can do very little. It knows what's going on, it knows what's going wrong, and all these meters talking to each other understand the problem. But until they can give a command to something that can actually make a decision on the distribution grid to take the transformer offline, to take the segment offline, to island that part of the grid, you can't do anything. So you have those meters have to be able to reach out in a protocol that the distribution control networks understand and say, we have a situation here, you need to do this, right? And we have to figure out where that happens. So, I think you're starting to see it in voltage regulation in certain places where you've got automatic tap changers and you've got voltage sensors in the meters, and you're bringing those back together, and it's a fairly simple illustration of it, but it's extremely powerful, right? Because if you have the right voltage, then you can actually optimize the amount of energy you're using. You can do a whole bunch of really good things for the grid, right? Does that answer the question?
So Paul, I'm learning here with the rest of us. So next to, let's say, the overall grid management, we have the microgrid management.
Yeah. Yeah.
And it's that where the meters start talking with each other that you will get, let's say, the most value in the microgrid management?
I think you would get a lot of, I mean, I think to some extent the microgrid management is one of the earlier places you're going to see that. I think in small islanded sections of grid, you hear about smart grid plans in places like India and you wonder why. You have so many other problems, why would you put smart meters out there? But a lot of it is these, they've got very remote towns and very remote locations where you might have an insufficient transmission line, but if you can manage the grid at a micro level, manage the load, then you can make best use of solar and storage and not overrun the local diesel generators to, you know, get people from 4 hours a day power up to 24 hours a day power or something like that. But I think there's also power in theft. I mean, if you really think about it, if you know the impedance change, sorry, I don't mean to be too geeky on the engineering side, but if you know the impedance change along a feeder, right? If you know that the voltage response and the response to a certain load is higher, much higher here than it is there, you know something's wrong in between those 2 points. And if you know something's wrong in between those 2 points, you can dispatch somebody. And it could be theft, it could be a high impedance fault, it could be any number of problems. In a high-rise building, it could be that the electrician who wired the building, you know, made a bad join and it's heating up. Now, it doesn't mean there's going to be a fire today, but you'd rather find out that you've got a hot joint now than when it catches on fire, right? So I think the opportunity to do things when the meters start to talk to each other, we probably haven't thought of all the options, I think, but yeah, I think there's a lot of value in being able to manage things at a very local level. Right?
Yeah, because I might be getting my electricity for my house from the solar panels of my neighbor.
Yes.
Right.
Yeah, that's probably happening right now. Well, you live in the Netherlands, so maybe not. But
maybe from a wind generator.
Exactly. Yeah, absolutely. And there are market mechanisms to settle that, and that's relatively easy at an energy level. But once you get down to the stability level in those grids, Germany and Australia have particular problems where they have so much solar that there's actually parts of the grid where they really can't manage it anymore because there's so much solar penetration. It changes the economics too. People with solar panels end up paying a whole lot less for their energy than they should, while people without solar panels end up double penalized. So one, they don't have a solar panel, and two, they end up paying more per kilowatt hour. So you have to understand, it also becomes a social and a fairness issue.
So we see the Internet of Things as a combination. So we see the things, the smart meters, not only starting to talk back to the center, but also to start talking to each other. And therefore we can really manage a local area. We see that with so much data, we cannot bring all the decisions back and have a human respond to every alert. Already going to any operations room, and you probably know that even better than I do, there are hundreds or thousands of alarms a day that people cannot manage anymore. Now multiply that, we're at 13 billion devices today. We think we will be at 50 billion devices in 2020. Humans cannot deal with all the alarms and all the alerts anymore. So we have to think in a different way of what is the role of the people in putting the bigger picture together versus the machines that can talk with each other, that can deal with the immediate issues, right? So that's where, let's say, you see IoT at work in the microgrid and taking it to an IoE level to manage the complete grid. And we haven't talked about really the substations yet. We've stayed at the transformer and smart meter level so far. But I think, Ronnie, you're going to talk a little bit about the substations and the wider grid, right? Any more questions for Paul? great dialogue. Thank you very much.